Lesson 5 in Moldex simulation. In this video I will go into the details about which results are important in the normal injection molding simulation. So the first step is that I have the results down here. In this case I have a mold base. We can solid mesh away with that. And then I have some cooling. Like that. The first thing we are going to look for is the filling results. And when you have the process determined and you are sure that the process is right, then you can start relying on the results. The first thing I'll do is I'll look into the filling, and for the filling is that is it possible to fill the part? Is the part filled totally up? So I go to results. I'll go over here so I have this view, and if I double click the filling, where's no, I can't remember where the log file is, but it's possible to see. Maybe it's here. Analysis, run to log flow, and then you can see if anything has gone wrong in this log file. What I start with is this slider up here, and I'm looking at the filling, and what I'm looking for is air traps. If I go up here, I can make a single color. I normally use that, and then what I'm doing is I'm going from one end in small steps. I can just take this forward. I can go in here and say fast. Started, it jumps in big steps. I can go in here and say slower, like this. Start the video, and it moves slower forward. What I'm looking for is air traps, because if you get air trapped, it will be squeezed together with this oily vapor in front of the melt, and if it can't get rid of the air, it will explode, and like a diesel effect, and that diesel effect will make an erosion in the mold, so you'll worn out the mold quite fast. So the important thing in the filling is to one of the important things is to get rid of the air. And the air, you can also display the air traps. This is a rough overview. You have to go through the filling step by step and use quite a long time for it, because if you forgot one air trap, sometimes you have to do nearly a whole mold again to get rid of the air, because then you have ejectors or cooling channels in the wrong positions. And from this, it's possible. I go to display again, air trap, away with that. And it's possible then in the results to make an animation of it. I do it like this. I'll just make a fast one. Normally I run with rotation 10 and frame per seconds 10, but I'll just make it very rough so it doesn't take any more time to do it. And then I can show the animation. It's just the AVI and you can see it's very rough. Okay, close. This one is located out if you go to the File Explorer under Report here. One up, close. The next step is you can see the air traps here. It's a still picture where you look at where you can see the air traps where they're coming. This one, for example, I'm a bit curious about that, so I'll go back to them. Yeah, it's not really an air trap. It's just some elements that make a small encapsulation of the air. It's not a real air trap. Okay. Oops, off the single color. And this is the air trap. By double clicking, of course, you get sometimes if I double click here, you get a display and a deviation of the results, a statistic. I go to weld line. A weld line is a visual. It shows where the melt comes in to vary if it meets each other and make a notch, or if you have what we call a weld, not a weld line, but a melt line. A melt line is when like here we have the weld line inside, and then it turns more or more over to a melt line. But if we go back to this one, it's only a melt line because we have a very steep angle between the two flow fronts, this one and this one, and it creates also a notch and a weak spot and also a visible spot. Then we want to avoid or secure that we are able to fill the part, and I do this by going into sprue pressure, and sprue pressure is the pressure at the end of the runner. So that's actually, if you have a small runner, you don't get the pressure drop in the runner. So if you want to rely on the pressure, you have to have a long the real runner system. But if you are under a certain level, it's not important that you have it. Of course, if a high filling pressure is around 1000, 1200, but it's possible sometimes up to 1600 bar in packing pressure. In this case, we have around 67 megapascal, like 70 megapascal, which is 700 bar. It's okay. Yeah, just secure that the machine is possible to inject, and normal machines can it's around 1800 bar to 2200 bar in injection pressure. And the injection pressure is a result of that you try to push the melt in to the mold with a certain velocity, a constant velocity, and if you do that, there's a pressure against this, and it's actually the pressure against this that you have to overcome, and therefore you have to apply pressure out here. The only place you can apply pressure is at the end of a melt. Yes. The next thing I'll dig into, I'll just close this up here. The next thing I'll dig into is the packing. And what I'm interested in is that I don't have any things that I cannot pack. So what I'm looking at first is the molten core, and the molten core is when you go from filling to packing, you go from a velocity controlled filling where you push the melt forward with a given velocity, and when you go to packing, you just apply a pressure up here, and when the plastic cools down, it shrinks, and then you can press more material into the part as it shrinks. But of course it freezes off the same time, so at a certain point you're not able to move the melt. So the molten core shows the material that are able to manipulate or press around in the mold. So you can change the molten core. This is the molten core at the end of pack. So if I, for example, choose here, we can see, okay, now we have possibilities to pack through the runner all over the part. What I don't want is some islands that are not able to pack. So I step forward in the packing here. Oh, suddenly here, this and this, they are not possible to pack. So they could get a bit a bad surface. And also over here, there's still a flow leader, a flow going in here. Yeah. Are there any other places? No. Ah, that's why there's a flow leader, because there's a screw tower underneath. And I'm stepping forward. Stepping. I'll just take that. And now you can see a bit back here around. Okay, now you can see it's actually not possible to pack this area down here. So you would expect higher shrinkage in this area than you have in this area, because if you cannot pack it, it shrinks without any back pressure, and you will not be able to fill in new material as it shrinks, and then of course it will shrink more. So what could you do to repair that? You could make flow leaders, so you have not necessarily the whole surface, but somehow a connection from the gate all the way down to this area. So secure that you're able to pack the part. If I go to end of pack, and then we have some sync mark indicator. The sync mark indicator tells you where could you expect some sync marks. I don't care about sync marks on a gate or runner. And you can see you'll get some sync marks in this area, but normally we don't care about sync marks on the back side, but it's a problem on the top side here, 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 and here. They will be visual, and you can go to this sync mark displacement, and you can see how much it's sinking down. The sync mark visibility is a matter of which surface is it on and so on. Very very shiny surface where you have a sync mark, it's very easy to see a sync mark. It's like looking down a side of a car. If there's just a small change in the surface due to a small stone have hit this surface and made a small bump in, then it's possible to see very easily. Then I also use this velocity vector, and I have to switch on the code runner again. Away with the curves, code runner curves. And the velocity vector tells me if there's any movement of the melt. By changing this, the lower value to 0.1, for example, I can see where are there any movement of the melt, and at the end of pack there's no. You can use this for finding out when is the gate freezing off. And then I use also this gate freeze, flow rate gate, close, and then I follow down on the bottom here when I have a flow rate that's going to get around 0. Let's say here, and then I can just move it up. You can say 0.01, that's nearly 0, and that's a packing time around 18 seconds. These are the most important packing conditions. Of course, the sync marks, if you want to get rid of them, you have to core out the area, or you have to also be able to pack them all through the packing time until they freezes off. Then I go to the cooling. And the cooling here, I'm just interested in, is the cooling efficient enough? Is the part cooled off? I don't care about the run. And we can see we have some hot spots here. But in general, I know that this part, you can also see that in the material wizard content eject temperature. That's what is actually concerning you, because we want the part as fast as possible out from this mold to be able to create a new one. So I can go into this ISO surface and I can see where is the hotspots. And again, you can see that the biggest wall thickness here is a hotspot. So sometimes you have to wait for that so you can eject the part before you can eject the part. And we also have this time to reach eject time. It just tells us that to reach the ejection time for the biggest wall thickness, we have to wait 41 seconds more. If you have a wall thickness, the cooling time is in second order. If you have a 2 millimeter a 1 millimeter wall thickness compared to a 2 millimeter wall thickness, the cooling time of a 2 millimeter wall thickness is 4 times as long as for one. So the real improvement of injection molding simulation is not improving the mold with better cooling or something, it's improving the part. Yes. The last thing I will comment on here is the warpage, because one thing is that you have made a CAD part that is correct and you can mount together with all the other parts, but when you run a injection molding process, something happens. Of course, because something happens with the plastic because you get differential shrinkage all over the part. What I start with is that I normally start with displacement, total displacement. I go to deformation, and then I can actually scale up here. Then I try to scale it maybe 5 times, like that. And then you can see, okay, it's falling in like that. That's not good, because maybe you'll make it's not able to fit to the bottom part. But this is one thing that you can visualize what's happening. Another thing is that you could how to find out what to do about it. All warpage is created due to differential shrinkage around the part. So if there's different shrinkage, you get different, you get warpage. And different shrinkage is not only in the length direction, also across the wall thickness. It's possible to insulate the displacement here in different directions. What I'm normally do is I'm looking at the volumetric shrinkage. Volumetric shrinkage is not linear shrinkage. Volumetric shrinkage tells you the shrinkage of a cube in 3 directions. If I look at this, I can use this clipping function up here, maybe turn it like that, inverse, and then I can go forward here. Let's see down here. It tells us the difference, the shrinkage. Through a wall thickness. It doesn't look at for much here, but if I, for example, change this one, double click on it for 2, you can see now there's a different shrinkage from outside to inside here, and that's giving this warpage of the wall falling in. And this wall falling in is, because I have of course a bit of experience in this, it's a result of the cooling that is not cool enough inside, so we have the same shrinkage inside. But I will just exit this. We also have some toys helping us with this. So if I go to this differential temperature effect, it actually tells me which effect of the warpage comes from the cooling properties in the mold. And you can see here, it's actually the red here, deformation. So you can say by cooling it down better from the inside, you could avoid this deformation. What about the shrinkage effect? This is the differential shrinkage effect. This is the warpage that appears due to different shrinkage. And let's have a look at that. It looks a bit different. You still have this inside, but what you most see here is that you have a smaller dimension here than in this end. And this is due to the packing conditions, that you couldn't pack this area down in the molten core, remember that. So if you were able to have a flow leader down here to be able to pack this, it would be much more uniform and with higher quality. So that's actually what simulation is about, finding the root cause for problems, repair them and make good parts. Let's just away with this. One thing I would also look at is the measure distance. And the measure distance is a way to measure the linear shrinkage in a mold, say. And you can see now we got a linear shrinkage of 0.431. And this linear shrinkage, if you make a mold, you choose one uniform shrinkage and then you make the mold. But if you don't achieve one uniform shrinkage in your plastic part because the design of the plastic part is wrong, then you get wrong, or you get bad quality, or parts out with high warpage. But this is a way to measure the shrinkage around the part, and if you had uniform shrinkage all over, you would not have any problems in the warpage. The shrinkage, if there was a linear shrinkage, was uniform all around, you could use the packing pressure just to if you go higher in packing pressure, you push more material in and you'll get a lower shrinkage. But if you want, let's say this one ABS is normally 0.6 of a shrinkage, then you want lower shrinkage here, but you want higher here. So if you want higher, you want lower shrinkage here and higher here. So if you make the packing pressure higher, you will overpack this, and this shrinkage will be even lower, but you will also go down in linear shrinkage here. So designing the plastic part is the most important. These was the results that I would show here.